What is nothing? On the surface, it sounds like a simple question, maybe even a trick one. Nothing is just the absence of anything, right? But as soon as you try to pin it down, it slips away. If you imagine an empty room, that's not really nothing. You still have air molecules, walls, light. Even if you strip away all matter, you're still left with space itself. And space, it turns out, is far from empty. At the tiniest scales, it seethes with activity. Energy fluctuations, quantum fields, and the potential for particles to appear and vanish. For thousands of years, philosophers, scientists, and theologians have wrestled with this puzzle. Ancient thinkers argued about whether a true void could exist at all. Experiments in the Renaissance showed that what seemed like empty space could be created, but even that vacuum turned out to hide unseen forces. And today, modern physics has made nothing one of the strangest and most important concepts in cosmology. The very origin and fate of the universe may hinge on what we mean by it. So what exactly is nothing? Is it a physical reality, or just a word we use for our ignorance? And if the universe came from nothing, what does that even mean? In this journey, we're going to peel back the layers of this question, from philosophy to quantum mechanics, to see whether true nothingness exists, or if the void of the universe is always filled with something. At first glance, asking why nothing matters might feel like a philosophical riddle. After all, why should we care about something defined by the absence of everything? But in science, the concept of nothing turns out to be one of the most important tools for probing the nature of reality. By questioning what it means for something not to exist, we get closer to understanding what existence itself is, how the universe began, and what its future might hold. One reason nothing matters is that it sets the baseline for everything else. Think of physics as a game where we try to define the rules of matter, energy, and space. To understand those rules, we need to ask, what would the universe look like if we stripped it bare, removing every star, planet, atom, and photon? That thought experiment is not just abstract, it's practical. Modern physics often compares the universe to its ground state, the lowest possible energy configuration. The question of what remains when we remove all excitations, all particles, and even all radiation is central to defining that baseline. And as we'll see, it turns out the ground state is not the same thing as nothing. Another reason is that nothing isn't just a limit case, it shows up in real physics. In cosmology, the vacuum plays an active role. When we talk about the expansion of the universe, we often refer to dark energy, the mysterious force driving galaxies apart faster and faster. Many physicists think dark energy is connected to the energy of empty space itself, a property of the vacuum. If that's true, then what looks like nothing could actually be the most dominant thing in the universe, making up about 70% of its total energy budget. Suddenly, nothingness doesn't look so empty. There's also the role of nothing in the origin story of the universe. When cosmologists talk about the Big Bang, they sometimes say the universe came from nothing. That phrase has been popularized in books and debates, but it's misleading if we don't unpack it carefully. Did the universe come from a literal void where no space, no time, and no physics existed? Or did it come from a quantum vacuum state governed by laws we only partly understand? The answer changes how we think about beginnings. If nothing can give rise to something, then maybe the boundary between the two is thinner than we imagine. Philosophers have long insisted that the idea of nothing is essential to thought itself. You can't define being without contrasting it with non-being. In ancient Greece, Parmenides argued that nothing cannot exist because to even think of it, you must treat it as something. His rivals, like the atomists Leucippus and Democritus, countered that a void must exist because atoms need space to move. Fast forward 2,000 years, and the same tension still plays out in physics, though with different tools. Instead of atoms and voids, we talk about quantum fields and vacuums. The question remains, is nothing a real, physical state, or just a necessary concept for structuring thought? Nothing also matters because it anchors our measurements. Take energy, for instance. When you say something has energy, you're measuring it relative to a baseline. But what is zero energy? In classical physics, it might mean no motion, no heat, no forces acting. In quantum physics, it's more complicated. The lowest energy state still has fluctuations, a jitter that cannot be removed because of the uncertainty principle. If we didn't have the concept of nothing as a reference point, We couldn't even define what something like motion or heat means. Nothing gives context to every measurement. On a practical level, engineers and scientists deal with nothing all the time. The invention of the vacuum pump in the 17th century allowed scientists to remove air from containers and study how objects fall, how sound travels, and how gases behave. This artificial nothing opened the door to modern physics. Today, particle accelerators rely on extreme vacuums, millions of times emptier than space, to smash protons together without interference. Space agencies design spacecraft to survive the near-perfect vacuum of interplanetary space, where even a single stray particle can damage sensitive instruments. So even when we say nothing, we are describing a condition with direct consequences for technology. But perhaps the deepest reason nothing matters is that it touches on the limits of our knowledge. If we could define a true nothing, we'd have to know what it means to have no laws, no space-time, and no possibility of anything. Yet physics, by definition, describes something. We can't run an experiment on a total absence of reality. So the quest to define nothing is also a mirror, showing us what we cannot know, or at least what our language struggles to capture. It's not only about answering scientific questions, it's about understanding the boundaries of science itself. In cosmology, this boundary shows up when we think about the far future. Imagine the universe expanding for trillions of years, stars burning out, black holes evaporating, and matter thinning into radiation. What's left then? Some call it the heat death of the universe, where energy spreads so thinly that no structures remain. At that point, what fills the universe might be indistinguishable from nothing, except it's not really nothing. It's an extremely thin soup of low-energy photons and neutrinos, fading into infinity. Again, we see how hard it is to pin down what nothing really means. The end of everything might not be an empty void, but an almost nothing that still resists being called truly nothing. On the flip side, nothing also frames our sense of beginnings. If the Big Bang wasn't the start, but rather a transformation from some prior state, then maybe there was never nothing, in the absolute sense. Instead, there was always some form of structure, however unfamiliar. Physicists working on quantum gravity often wonder if space-time itself can fluctuate into existence from a deeper level of reality. If that's the case, then nothing is not a void, but a hidden backdrop we can't yet describe. And that means the universe might not need an explanation for how something comes from nothing, because nothing, in the strictest sense, never existed. Finally, nothing matters because it shapes how we think about our own existence. The idea that the universe could emerge from nothing can feel unsettling, as if it undercuts meaning or purpose. But it can also be liberating. If nothing is not an absence but a kind of potential, then existence is less a miracle against impossible odds, and more a natural unfolding of what nothing can do. In that sense, studying nothing is also about finding our place in the cosmos. We're trying to understand not just why there is something rather than nothing, but what nothing itself actually is. Long before science could run experiments with vacuum pumps or particle accelerators, people were already asking whether nothing could exist. In fact, the question of nothingness is one of the oldest in philosophy. It's not hard to see why, once you start thinking about existence, about what it means for something to be, you inevitably bump into the opposite. What does it mean for something not to be? If everything we experience is something, then how can we even imagine nothing without turning it into another something in our minds? The earliest debates in Western thought about nothing trace back to ancient Greece in the 5th century BCE. One of the most influential figures was Parmenides of Elea. He argued that nothing was impossible. To speak of it, to think of it, already gave it some form of existence. For Parmenides, reality was a single, unchanging, indivisible whole. Change, motion, and void were illusions of the senses. If there is being, then non-being cannot exist at all. It's a radical view. The universe is full, solid, and eternal, with no room for emptiness. That view was challenged by another group of thinkers, the atomists, most famously Leucippus and Democritus. They claimed that reality was made of tiny, indivisible particles, atoms moving through empty space. The void was not only real but necessary. Without it, motion would be impossible. Imagine trying to shuffle a deck of cards with no gaps between them. They couldn't move past each other. In the same way, atoms needed empty space to collide, combine, and separate. For Democritus, the void was as real as the atoms themselves. Instead of denying nothing, he elevated it to a fundamental part of existence. This clash between those who said nothing cannot exist and those who said it must exist set the stage for centuries of debate. Aristotle, writing later, sided more with Parmenides. He believed nature abhors a vacuum. In his view, emptiness was impossible because space was always filled with some medium, whether air or some other substance. If you remove air from a vessel, something else must rush in to take its place. Otherwise, motion and causation would break down. Aristotle's arguments became dominant in Western thought for almost 2,000 years, reinforcing the idea that the void was a fiction. Meanwhile, outside of Greece, other traditions approached the idea of nothingness differently. In Eastern philosophy, especially in early Buddhist thought, emptiness, shunyata, did not mean a literal void, but rather the absence of inherent, permanent essence in things. Everything exists only in relation to other things, and clinging to the idea of fixed existence is a source of suffering. This is a very different approach. Nothingness here isn't a physical vacuum, but a description of how reality is structured. It highlights the difference between metaphysical and physical uses of the word nothing. In India, Jain philosophers argued that reality consisted of substances with different attributes, and the concept of void was acknowledged but treated cautiously. In China, Taoist texts sometimes celebrated emptiness as a source of potential. Laozi, in the Tao Te Ching, wrote about the usefulness of what is not there, the empty space inside a bowl, or the hole in a wheel's hub. These examples show that in many traditions, nothingness was not feared, but embraced as a necessary counterpart to being. When medieval thinkers inherited the Greek legacy, they folded these debates into theology. In Christian philosophy, the concept of creation ex nihilo, creation out of nothing, became central. If God created the universe, it had to come from nothing, since nothing existed before God's act. But this raised its own puzzles. If nothing truly means no space, no time, no laws, then how could creation even take place? Theologians often resolve this by saying that nothing is not a real state, but rather the absence of created things, with God existing beyond it. This kept the discussion alive, but also shifted it away from natural philosophy and toward faith. During the Renaissance, the rediscovery of ancient texts revived the atomist view. Thinkers like Giordano Bruno and later Galileo were more open to the possibility of empty space. But it wasn't until experiments with barometers and vacuums in the 17th century that the philosophical arguments began to be tested. Even then, the debate wasn't just scientific. Philosophers like Descartes argued that space and matter were inseparable, meaning a true vacuum couldn't exist. Others, like Pascal, countered with experimental results showing otherwise. The tug-of-war between philosophy and physics was already underway. The interesting thing about these early debates is how much they still echo in modern physics. Parmenides' claim that nothing cannot exist has a modern cousin in quantum field theory, where empty space always has activity and structure. Democritus's insistence on the void as real has its parallel in our understanding of space, as the arena in which particles and forces play out. Even Aristotle's resistance to the vacuum has a strange echo in the way we now think about the fabric of space-time. Perhaps not a substance, but not nothing either. What these philosophical roots show is that nothing has never been a neutral idea. It's always been entangled with questions about motion, change, causation, and even meaning. When we say nothing, we're not just pointing to an empty spot in reality. We're drawing lines around what we think reality is allowed to contain. The void has always been as much a mirror for human thought as it is a concept about the universe. And this is why the history of nothing matters. Before we can talk about the vacuum in physics or the quantum fluctuations of empty space, we have to understand how people wrestled with the very possibility of absence. From the Greeks to the Buddhists, from Christian theologians to Renaissance natural philosophers, nothingness has been both feared and embraced, denied and affirmed. It has been a limit case for logic and a canvas for imagination. And those ancient tensions still shape the way scientists and philosophers approach the question today. When it comes to the history of ideas about nothingness, few figures had as much influence as Aristotle. Writing in the 4th century BCE, he built one of the most comprehensive philosophical systems of the ancient world. And for him, the idea of a void, a true empty space, was not just doubtful, it was impossible. His rejection of the void shaped scientific thought for nearly 2,000 years, slowing the acceptance of emptiness as a real physical condition. To understand why, we need to unpack his reasoning. Aristotle began with a simple principle: everything in nature has a purpose, or a natural tendency. Stones fall because their nature is to seek the centre of the earth. Fire rises because its nature is to seek the heavens. Motion, in Aristotle's world, was always explained by some cause acting on the object, either internally or externally. That meant that movement required interaction. So what would it mean for something to move in a void, with no medium to act upon it? For Aristotle, this was a contradiction. A void couldn't help explain motion. It would make motion inexplicable. He argued that if a void existed, movement would become paradoxical. In an empty space, why would something move at one speed rather than another? With no medium to provide resistance, an object could theoretically travel infinitely fast. That, to Aristotle, was absurd. Nature, he believed, avoided absurdities. Therefore, the conclusion was simple: a void does not exist. The phrase often attributed to him, horror vacui, nature abhors a vacuum, summarized this conviction. Wherever you try to create emptiness, something else must rush in to fill it. Aristotle's reasoning also rested on his understanding of place. For him, place was not just a container, but an essential part of what something is. Every object had a natural place it sought: earth at the centre, water above it, air above that, and fire above the air. Space was not an independent arena that could exist without objects. It was defined by the relationships of things to one another. The idea of a place without things, a bare container, didn't make sense in his framework. You couldn't have space without matter, because the two were conceptually intertwined. This view was enormously influential. Later Greek and Roman thinkers, especially those who followed Aristotle, carried his rejection of the void into the mainstream of philosophy. Even when atomist ideas survived on the margins, Aristotle's system became the dominant framework for medieval thought. His philosophy was woven into Christian theology, Islamic scholarship, and European universities. To challenge Aristotle wasn't just to challenge a philosopher, it was to challenge the structure of knowledge itself. What's striking is how plausible Aristotle's reasoning seemed without modern tools. If you live in a world where all motion appears to involve pushing through a medium, boats moving through water, birds through air, fish through the sea, then the idea of motion in emptiness does look nonsensical. Without the ability to create a vacuum and test it, the claim that voids can't exist is hard to dispute. In fact, it fit neatly with everyday experience. Try to suck liquid through a straw, and it only works because air pushes down on the drink. For Aristotle's followers, that was proof enough that emptiness was impossible. Of course, we now know his argument doesn't hold. Objects don't require a medium to move. They move because of inertia, as Newton later described. Speed doesn't depend on resistance. It depends on forces applied. And there's no paradox in motion through empty space, because physics allows for consistent rules even in a vacuum. But from Aristotle's perspective, those ideas would have sounded bizarre. Without the concept of inertia, the void really did seem to break the logic of motion. Another subtle reason Aristotle rejected the void is that he saw it as philosophically useless. It explained nothing. If a void existed, it wasn't a substance, a force, or a cause. It was simply the absence of all those things. For a thinker who wanted to give reasons for everything, that was unsatisfying. He preferred a universe that was full, continuous, and purposeful rather than one where gaps and emptiness played a role. In this way, his metaphysical commitments, his desire for a tidy, meaningful cosmos, reinforced his physical arguments. The phrase "nature abhors a vacuum" lived on long after Aristotle. Medieval thinkers repeated it almost as a law of reality. And in some ways, early experiments seem to support it. Suction pumps, for instance, failed to raise water higher than about 10 meters. This was taken as evidence that a perfect vacuum couldn't exist, until later scientists like Torricelli realized it was due to air pressure, not horror vacui. The persistence of Aristotle's view shows how powerfully a philosophical system can shape interpretation. For centuries, people saw what they expected to see, a universe that refused emptiness. What makes Aristotle's rejection of the void so important is not that he was wrong, it's that his reasoning defined the terms of the debate for centuries. To this day, when physicists describe the quantum vacuum as not really empty. They are in some sense echoing his suspicion that a true nothingness is impossible. Modern physics has replaced horror vacui with more precise concepts, but the instinct that emptiness is unstable, unnatural, or illusory still lingers. In that sense, Aristotle's ghost is still with us whenever we ask whether nothing can truly exist. For nearly 2 millennia after Aristotle, the idea that nature abhors a vacuum dominated science and philosophy. The notion of a true void was treated almost like a superstition, an impossibility, something that reality itself would resist. But in the Renaissance and early modern period, this conviction finally began to crack. And it cracked not because of abstract arguments, but because of experiments. One of the key turning points came in the early 17th century with a very practical problem. How do you pump water out of a mine? Miners had long used suction pumps to lift water, but these devices seemed to hit a strange limit. No matter how strong the pump, water couldn't be raised more than about 10 meters. Engineers thought it was a mechanical issue. But the Italian scientist Galileo Galilei suspected something deeper was going on. He suggested that the limit wasn't in the pump but in nature itself. Perhaps water could only rise so far because the suction created a vacuum above the water, and nature, following Aristotle's rule, simply didn't allow a complete void. It was Galileo's student Evangelista Torricelli who decided to test this idea more rigorously. In 1643, he filled a glass tube with mercury, a much denser liquid than water, sealed one end and inverted it into a basin. The mercury column stayed up, but only to a certain height, leaving a space at the top of the tube. This Torricellian vacuum was shocking. The empty space seemed to have nothing in it. No air, no liquid, nothing visible at all. It was the first real demonstration of a sustained vacuum on Earth. Nature had not rushed in to fill it. Instead, the column of mercury was balanced by air pressure pushing down on the basin. Torricelli's experiment did more than show that vacuums could exist. It redefined how scientists thought about air itself. For Aristotle, air was a kind of weightless nothingness that filled the gaps. Torricelli revealed it had weight and exerted pressure. The nothing at the top of his tube became evidence that the atmosphere itself was a physical substance pressing down on us. This single experiment shifted the question of nothingness from philosophy to physics. The work didn't stop there. Blaise Pascal, intrigued by Torricelli's results, carried barometers up a mountain in France to see if the mercury level would drop with altitude. It did, showing that air pressure decreased at higher elevations. This confirmed that the empty space above the mercury wasn't an illusion, but a real vacuum maintained by the physical force of the atmosphere. Nature wasn't abhorring a vacuum. It was air pressure preventing one from forming freely. Soon after, vacuum pumps were developed, most famously by Otto von Guericke in the mid-17th century. Guericke invented a pump that could remove air from a chamber, creating a man-made vacuum. To demonstrate the power of air pressure, he conducted a dramatic experiment in Magdeburg in 1654. He joined two large hemispheres together, pumped the air out from inside, and showed that teams of horses could not pull them apart. The reason wasn't that something inside was holding them together, it was that air pressure outside was pushing them with enormous force. The experiment became legendary, a vivid spectacle showing that vacuums could be created and that they behaved according to physical laws. These experiments undermined Aristotle's horror vacui, but didn't immediately settle the question of what a vacuum really was. Some philosophers, like René Descartes, still argued that space and matter were inseparable. To them, even if you removed air, some subtle medium must remain to transmit forces and light. Others, more aligned with the atomist tradition, embraced the vacuum as truly empty space, in which particles could move freely. The debate was far from over, but for the first time people had evidence they could point to, rather than just abstract reasoning. The experimental study of vacuums also led to practical discoveries. Scientists realised that in low-pressure environments, sound doesn't travel well, since it needs a medium like air to carry vibrations. They also saw that flames struggled to burn, and animals couldn't survive inside evacuated chambers. These findings made clear that nothing could have real, measurable effects on the behaviour of matter. The void wasn't just a philosophical curiosity, it had consequences for everyday phenomena. Perhaps the most important legacy of the Renaissance experiments was the shift in mindset. Nothingness stopped being purely an abstract puzzle and became a scientific question that could be tested, measured, and argued with data. The invention of instruments like barometers and pumps gave researchers new ways to probe the limits of emptiness. The void was no longer just a thought experiment, it was a laboratory reality. By the end of the 17th century, the groundwork had been laid for a new understanding of space. Isaac Newton would go on to describe space as an independent arena in which matter and forces operate, a kind of absolute stage that could exist even if no actors stood upon it. That idea owed much to the experimental breakthroughs of Torricelli, Pascal, and Guericke, who showed that emptiness could exist without collapsing reality. In short, the Renaissance marked the moment when the void began to leave the realm of Aristotle's metaphysics and enter the world of physics. For the first time, nothing could be created, studied, and even harnessed. And once that door was opened, it became impossible to close. From then on, nothing was not just a philosophical problem, but a physical frontier. By the 18th and 19th centuries, the vacuum was no longer treated as an impossibility. Experiments had shown that nothing could be made in the lab, at least in the sense of removing air and other obvious matter. But scientists quickly realised that even when you remove all gases, light still passes through, and forces like gravity still act. The vacuum, it turned out, wasn't completely empty. It was a stage on which phenomena still played out. This insight opened the door to a much stranger discovery, that the vacuum might be less of a void and more of a hidden structure. During the 19th century, physicists believed this structure was the ether, an invisible medium that filled all of space. Light, understood as a wave, needed something to ripple through, just like sound needs air or water. The ether seemed like a natural solution. It was the invisible substance pervading the vacuum, giving space its properties. But in 1887, the famous Michelson-Morley experiment tried to detect the Earth's motion through the ether and found nothing. The ether simply wasn't there. This failure was one of the seeds of Einstein's special relativity, which showed that light doesn't need a medium at all. It travels through space itself. Einstein's work reframed the vacuum again. In relativity, space isn't an empty container, but a dynamic fabric, space-time, that bends and curves under the influence of matter and energy. Even if you strip away all particles, space-time remains. In this sense, the vacuum is already not nothing but something, a physical structure with properties. Gravity can act across it, light can move through it, and its geometry can change. The biggest transformation, though, came with quantum mechanics in the 20th century. Physicists discovered that particles like electrons and photons aren't just little beads moving around in space. They're excitations of underlying fields that extend throughout the universe. Every kind of particle, electron, quark, photon, corresponds to a field that exists everywhere, all the time. In this picture, the vacuum is not the absence of particles, but the state where these fields are in their lowest possible energy. That sounds deceptively simple, but it's profoundly strange. The quantum vacuum is not a calm, featureless backdrop. Because of the uncertainty principle, fields in their lowest energy can never be perfectly still. They fluctuate, producing what physicists call vacuum fluctuations. These fluctuations mean that even in an apparently empty region of space, the fields are jittering with energy. And sometimes, that energy can momentarily produce pairs of particles and antiparticles, which pop into existence and then annihilate almost instantly. To an observer, the vacuum is alive with activity at the smallest scales. This leads to one of the most counterintuitive insights of modern physics. The vacuum is not truly empty. It has energy, structure, and even measurable effects. One famous example is the Casimir effect. If you place two uncharged metal plates extremely close together in a vacuum, quantum fluctuations of the electromagnetic field are restricted between them. This creates a tiny pressure that pushes the plates together. It's a real, measurable force caused entirely by the properties of the vacuum. Nothing, it turns out, can push. Another consequence of this view is that the vacuum can define what counts as something. A particle is just an excitation of a field above its vacuum state. In a sense, matter is ripples on the surface of a deeper sea, the quantum fields. The vacuum is the ocean itself. Without it, there would be no particles to ripple into existence. In this way, the vacuum is not the opposite of something. It's the foundation of everything. This redefinition has enormous implications for cosmology. If the vacuum has energy, It might explain why the universe is expanding faster and faster. This vacuum energy could be what we call dark energy, the mysterious component driving cosmic acceleration. But here lies a puzzle. When physicists calculate how much energy the quantum vacuum should have, the number comes out absurdly huge, over 100 orders of magnitude, larger than what observations suggest. This mismatch, sometimes called the vacuum catastrophe, is one of the biggest unsolved problems in physics. Somehow the vacuum is energetic enough to shape the cosmos, but not nearly as energetic as theory predicts. The quantum view also changes how we think about beginnings. If space can't be truly empty, then the idea of a universe from nothing takes on a new twist. Perhaps the Big Bang emerged not from a void, but from a quantum vacuum, where fluctuations could spark inflation and seed the cosmos. That kind of nothing isn't a blank void, but a simmering field full of potential. In other words, what we call nothing may be the most fertile state imaginable. So in just a few centuries, the vacuum transformed from Aristotle's impossibility to Torricelli's experimental curiosity to Einstein's curved space-time, and finally to the quantum vacuum, a sea of restless fields that underpins everything. The lesson is that nothing keeps turning out to be something, just deeper and stranger than before. Far from being irrelevant, the vacuum has become central to our picture of reality. It is the backdrop against which matter, energy, and even the expansion of the universe play out. And the more closely we study it, the more nothing looks like the hidden engine of everything. If the quantum vacuum is never truly empty, the natural question is, what exactly fills it? The short answer is energy, fluctuations, and, most intriguingly, particles that exist only for a fleeting moment. These are known as virtual particles, and together with the restless geometry of space-time itself, they give rise to what physicist John Wheeler once called quantum foam. To see why virtual particles appear, we need to go back to the uncertainty principle. In quantum mechanics, you can't pin down both the energy of a system and the time over which that energy is defined with perfect precision. There's always a trade-off. This loophole means that for very short timescales, energy can borrow against the vacuum as long as it's paid back quickly. That temporary burst of energy can take the form of a particle-antiparticle pair appearing out of nowhere. An electron and a positron, for example, can flash into existence, separate briefly, and then annihilate each other, leaving the vacuum as it was. These aren't particles in the ordinary sense. They can't be directly observed in the same way as electrons in an atom or photons from a lamp. Instead, they show up indirectly in the mathematics of quantum field theory and in the measurable effects those calculations predict. A good example is the Lamb shift, discovered in hydrogen atoms. The energy levels of electrons in hydrogen were slightly different from what basic theory predicted. The correction came from the influence of virtual particles in the vacuum, subtly shifting the electron's behavior. Without the jittering activity of the vacuum, the hydrogen spectrum would look different. Another striking case is Hawking radiation. Near the event horizon of a black hole, the vacuum fluctuations become so extreme that one particle of a virtual pair can fall into the black hole while the other escapes. To a distant observer, it looks as if the black hole is emitting radiation, slowly losing mass over time. This remarkable process relies entirely on the reality of virtual particles in the quantum vacuum. What started as a theoretical curiosity now explains how black holes might eventually evaporate. The presence of virtual particles also plays a role in forces. In quantum electrodynamics, the force between two charged particles can be understood as the exchange of virtual photons. They aren't real photons flying back and forth, but temporary disturbances in the electromagnetic field that mediate the interaction. The same idea extends to the strong and weak nuclear forces, where virtual gluons and W and Z bosons appear in the calculations. In this sense, the fundamental forces themselves are tied to the existence of these ghostly, short-lived entities. But if virtual particles reveal the vacuum's activity, quantum foam shows how restless space-time itself may be. Wheeler coined the term in the 1950s to describe what might happen if you zoomed into the Planck scale, the unimaginably tiny length of about 10 to the minus 35 power meters, where quantum effects of gravity can't be ignored. At that scale, space-time might not look smooth and continuous. Instead, it could be a frothing, turbulent sea of tiny distortions. Little bubbles of space could pop in and out of existence, Wormholes could briefly connect distant points, and the geometry itself could fluctuate wildly. We don't yet have direct evidence of quantum foam. It remains a theoretical idea, born from trying to merge quantum mechanics with general relativity. But it captures an important lesson. If the vacuum is full of quantum activity at the particle level, it might be equally chaotic at the level of space-time. Nothing, when pushed to its limits, may look less like a calm void and more like a storm. This picture challenges our intuition in profound ways. Most of us grow up thinking of empty space as a blank canvas, a quiet background. But quantum field theory flips that image. The vacuum is not quiet, it's buzzing. Particles constantly appear and vanish. Fields fluctuate even in their lowest energy state, and space-time itself may writhe with microscopic turbulence. Far from being nothing, the vacuum is the most dynamic something imaginable. The concept of virtual particles also raises a philosophical puzzle. If they can't be directly observed, in what sense do they exist? Are they real, or just a convenient mathematical tool? Physicists tend to be pragmatic about this. If the calculations work and the predictions match experiments, then virtual particles are useful, and in that sense, real enough. But whether they exist in the same way as electrons or protons is still debated. Some physicists argue they're just bookkeeping devices in equations. Others see them as genuine, if fleeting, features of reality. Either way, their effects are undeniable. The idea of quantum foam takes that debate a step further. If space-time itself is bubbling and fluctuating at the smallest scales, then the fabric of reality isn't fabric at all. It's foam, unstable and constantly changing. That raises deep questions about what it means to talk about space, time and emptiness. At what point does the very concept of place break down? So when we talk about nothing at the quantum level, we're really talking about one of the busiest, most crowded concepts in physics. Virtual particles fill the vacuum with fleeting activity. Quantum foam hints that space-time itself may be restless. And together they remind us that nothing is never truly nothing. Instead, it's a seething foundation upon which everything else rests. By the time physicists accepted that the quantum vacuum was far from empty, they began asking what all this hidden activity might mean for the universe as a whole. The answer turned out to be both exciting and troubling. If the vacuum has energy, real, measurable energy, then the energy should have gravitational effects. In other words, nothing could help shape the cosmos. The first hints of this idea appeared in Albert Einstein's equations of general relativity. In 1917, when he applied his theory of gravity to the entire universe, he realized something odd. According to his equations, a universe filled only with matter would either expand or contract. It couldn't stay static. But at the time, most scientists believed the universe was eternal and unchanging. To fix this, Einstein added a new term, the cosmological constant. This acted as a kind of repulsive force built into space itself, counteracting gravity and keeping the universe stable. Einstein later called this his greatest blunder, after Edwin Hubble discovered in 1929 that the universe was expanding. A static universe was a false assumption, but the idea of a repulsive energy inherent to space didn't disappear. In fact, it resurfaced decades later, under a new name, vacuum energy. The reasoning goes like this: if quantum fields are never truly at rest, then even their lowest energy state, the vacuum, has some leftover energy. Unlike ordinary energy, which is concentrated in particles or radiation, vacuum energy is spread evenly throughout space. And because space itself is expanding, the total amount of vacuum energy grows as the universe grows. Instead of thinning out, it maintains a constant density. This is profoundly different from matter and radiation, which get diluted as space stretches. The potential consequences are enormous. A vacuum with energy would act gravitationally not like mass, which pulls things together, but like a kind of anti-gravity, pushing things apart. And in the late 1990s, astronomers found compelling evidence that this is exactly what's happening. Observations of distant supernovae showed that the universe's expansion isn't slowing down, as many expected, but speeding up. Some unseen force is driving galaxies apart faster and faster. This force is now called dark energy, and the leading explanation is that it's tied to vacuum energy. In modern cosmology, dark energy makes up about 70% of the total energy content of the universe. That means most of what shapes the cosmos is not stars, galaxies, or even dark matter, but something associated with the energy of empty space itself. The universe is, quite literally, dominated by nothing. But here's where the puzzle deepens. When physicists try to calculate the amount of vacuum energy predicted by quantum field theory, the result is staggeringly wrong. The calculations give a value 10 to the power of 120 times larger than the observed dark energy. This discrepancy is so vast it's often called the vacuum catastrophe, one of the worst mismatches between theory and observation in science. It suggests that either our understanding of the vacuum is incomplete, or something cancels out most of its energy in ways we don't yet grasp. Some theories suggest that the vacuum energy is renormalized or balanced out by other contributions we don't fully understand. Others propose that dark energy isn't vacuum energy at all, but something more exotic, like a new dynamic field that changes over time. Still others wonder if our equations break down on cosmic scales, requiring a new approach to gravity itself. None of these ideas has been confirmed, which is why dark energy remains one of the biggest open mysteries in physics. What's striking is how these questions tie back to our original theme of nothingness. The expansion of the universe is being accelerated, not by matter or radiation, but by whatever lurks in the vacuum. In other words, the fate of the cosmos may be dictated by what happens in empty space. The concept of nothing has gone from a philosophical puzzle to a measurable, universe-shaping force. Dark energy also forces us to rethink beginnings. During cosmic inflation, a brief explosive expansion thought to have occurred right after the Big Bang, the universe was likely driven by something similar to vacuum energy. In that case, it wasn't just pushing galaxies apart, but stretching tiny quantum fluctuations into the seeds of all structure: stars, galaxies, and clusters. In both the earliest and the present-day universe, it seems the vacuum itself is the engine of change. For scientists, this makes the problem of vacuum energy urgent. It's not just a detail of particle physics, it's central to cosmology. If we can figure out why the vacuum has the energy it does, we might learn why the universe expands the way it does, whether it will keep accelerating forever, and what its ultimate fate will be. Right now, the only thing clear is that nothing is the most powerful something in the cosmos. So from Einstein's cosmological constant to today's dark energy, the story has come full circle. What was once dismissed as a blunder is now at the heart of our understanding of the universe. And once again, the vacuum, the supposed realm of nothingness, turns out to be the key player. When cosmologists talk about nothing, they don't mean the kind of nothing we imagine in everyday life: an empty room, a blank canvas, or even the space between stars. Instead, they mean something much stranger, a state that might have existed before the universe began, or a condition that still underpins cosmic evolution. In cosmology, nothing has always been at the centre of our efforts to explain where everything came from. One of the most striking ideas is cosmic inflation. This is the theory that, in the earliest fraction of a second after the Big Bang, the universe expanded exponentially, doubling in size again and again at an almost unimaginable rate. This expansion was driven by a high-energy, vacuum-like state, sometimes called a false vacuum. In this state, space itself was filled with vacuum energy so intense that it acted like a repulsive force, blowing the universe up by an enormous factor in a blink of time. Inflation explains several puzzles that otherwise don't make sense. For example, why does the universe look so uniform in all directions? Why does space appear flat rather than curved? Inflation smooths everything out, ironing away irregularities and leaving behind a vast, nearly homogeneous cosmos. But it also magnifies tiny quantum fluctuations in the vacuum into macroscopic ripples. These ripples later became the seeds of galaxies, stars, and clusters. So in a very literal way, everything we see today, every star in the night sky, traces its origin to quantum activity in an almost nothing state. This raises a profound question. Does inflation mean the universe came from nothing? Some physicists suggest that the Big Bang wasn't an explosion of matter, but a transition from one vacuum state to another. If that's the case, the before may not have been nothing in the absolute sense, but rather a different kind of vacuum. The Big Bang could then be seen not as a creation event, but as a transformation of a quantum field, shifting from a false vacuum to a lower energy vacuum. What looks like something from nothing is really something from a different kind of something. Still, some cosmologists argue that a true nothing might be possible. In certain models, the laws of physics themselves could emerge from a state with no space, no time, and no fields, what you might call absolute nothingness. But here language starts to fail. If there's no time, then talking about before the universe is meaningless. If there's no space, then saying the universe appeared makes little sense. We're left with equations that hint at origins but don't map neatly onto our words. This is why nothing in cosmology often serves as a placeholder. When we say the universe may have come from nothing, we usually mean it came from a vacuum-like state that's still governed by physics. It's not nothing in the philosophical sense, but it's as close as physics can get to stripping everything away. Whether absolute nothing is even a coherent idea is an open question. Another way cosmology wrestles with nothing is through the possibility of multiple universes. If inflation can happen once, maybe it can happen repeatedly. In some theories, different regions of space-time undergo inflation independently, creating bubble universes within a larger multiverse. Each bubble could have its own laws of physics, born from fluctuations in its vacuum state. In that picture, our universe is just one bubble, and the nothing outside it is not truly empty, but a frothing sea of quantum fields where other universes are constantly budding off. Even within our own universe, the role of nothing remains central. The expansion we see today, driven by dark energy, may be the echo of that early vacuum energy. In both cases, the void is not a passive backdrop, but the engine of cosmic evolution. If inflation explains the beginning and dark energy explains the present acceleration, then the vacuum is bookending the story of the universe. But this picture also leads to unsettling possibilities. If the vacuum can change states, what's to stop it from doing so again? Some physicists worry about vacuum decay, where our current vacuum is only metastable, not the lowest possible energy state. If that's true, then someday, somewhere, a bubble of true vacuum could form, expanding at nearly the speed of light and rewriting the laws of physics inside it. From the perspective of our current universe, it would mean annihilation in an instant. From the perspective of physics, it would mean transition to a new reality. In this sense, nothing is not only about beginnings, but also about possible endings. Cosmology shows us that nothing is never simple. It might mean the quantum vacuum seething with fluctuations. It might mean a false vacuum driving inflation. It might mean the complete absence of space and time, though whether that's a coherent state is debatable. In every case, nothing isn't just absence. It's potential. It's the condition that allows the universe to exist, to evolve, and maybe to end. So when we ask whether the universe came from nothing, we're really asking, which version of nothing? A quantum vacuum with energy, a false vacuum driving inflation, or a true nothing beyond even the laws of physics? Cosmology doesn't give us a final answer yet, but it makes one thing clear. The universe owes its existence to the properties of the void, and that means understanding nothing is key to understanding everything. The deeper physicists dig into the concept of nothing, the stranger it gets, and the more contradictions appear. On one hand, the vacuum is central to modern theories of the universe. On the other, it produces some of the most puzzling mismatches between theory and observation in all of science. The story of nothing isn't just about breakthroughs, it's also about paradoxes that we still haven't resolved. The most famous of these is the so-called vacuum catastrophe. As we saw earlier, quantum field theory predicts that the vacuum should have a certain amount of energy based on all the possible fluctuations of quantum fields. But when you actually run the numbers, the result is absurd. The predicted vacuum energy density is around 10 to the 120 times larger than the amount of dark energy inferred from cosmic expansion. To put that in perspective, it's the biggest discrepancy between theory and measurement in the history of physics. Something is clearly off, but we don't know what. One possibility is that our method of calculation is flawed. Quantum field theory works extremely well for describing particles and forces, but maybe it's not the right tool for describing the vacuum on cosmic scales. Another is that something cancels out most of the vacuum energy. Some theories propose that positive and negative contributions from different fields balance each other almost perfectly, leaving only a tiny remainder. But if that's true, why is the cancellation so precise? It feels like fine-tuning, which makes physicists uneasy. Then there's the paradox of defining nothing at all. If the vacuum is full of fields and fluctuations, is it really nothing? Or is it simply the lowest energy something we know about? Some philosophers argue that physics can't touch true nothingness, because physics always describes something: laws, fields, structures. When scientists say nothing, they're really describing a stripped-down version of reality, not the absolute absence of it. The paradox is that the more physics explains, the harder it becomes to say whether we've ever actually touched the idea of nothing. Another puzzle is whether the vacuum is stable. The Higgs boson, discovered in 2012, gives mass to fundamental particles through its field, which also contributes to vacuum energy. Measurements of the Higgs mass and other parameters suggest that our current vacuum may be only metastable. That means it's not the lowest possible energy state, but a temporary plateau. If so, the universe could one day tunnel into a lower energy vacuum, triggering a bubble of true vacuum that expands at the speed of light. Inside that bubble, the laws of physics would be completely different. From our perspective, everything would vanish in an instant. This isn't something we need to worry about tomorrow. Calculations suggest such an event would take longer than the current age of the universe, but it highlights the unsettling possibility that nothing could be both the foundation of our reality and its undoing. The vacuum isn't just background scenery, it's an active player that could dictate how long the universe lasts. There's also the paradox of measurement. Many of the effects of the vacuum, like the Casimir effect or the Lamb shift, are subtle, only detectable with precise instruments. Yet their existence proves the vacuum is not empty. At the same time, we can't directly observe virtual particles or quantum foam, only their indirect consequences. This raises the question: is the vacuum real in the same sense as matter and energy, or is it just a convenient way of talking about effects? Different physicists answer this differently, depending on how literal they think our mathematical models should be. Finally, there's the paradox of beginnings. If the universe came from nothing, what does that mean? If nothing already has laws of physics, quantum fields, fluctuations, or the possibility of tunneling, then it isn't nothing at all. But if nothing means the absence of laws, then how could anything emerge from it? Some cosmologists argue that we can never answer this question because our language and equations are built to describe something, not nothing. Others suggest that asking what was before the universe is like asking what's north of the North Pole, a question that doesn't make sense because it assumes a framework that doesn't exist. These paradoxes don't mean science is failing. They mean we're probing the limits of what science can describe. Just as earlier generations wrestled with whether the void could exist at all, we now wrestle with whether nothing is stable, measurable, or even definable. Each paradox forces us to sharpen our concepts and test our theories more carefully. And in that sense, the problems of nothing are as valuable as the solutions. At the very least, these puzzles remind us of one simple truth: nothing is complicated. What seems like the simplest idea, absence, turns out to be the most difficult to pin down. And the fact that entire branches of physics now depend on how we define and understand nothing shows just how central it really is. If quantum field theory already makes the vacuum unstable, some theories go even further. They suggest that space-time itself might not be permanent. Instead of just particles or fields decaying, the very fabric of the universe could, in principle, collapse into nothing. This dramatic idea is sometimes called a bubble of nothing. The concept was introduced in 1982 by physicist Edward Witten, working in the context of higher dimensional theories. In certain models inspired by string theory, space-time isn't just the 3 dimensions of space and one of time that we experience. It may include extra dimensions, curled up so small we don't notice them. Witten showed that in such a setup, it's possible for those extra dimensions to pinch off. When that happens, the region of space-time essentially disappears, creating a bubble of nothingness that expands outward. Inside the bubble, there's literally no space, no time, and no physical laws. It's not a new kind of vacuum or a different phase of matter. It's the absence of reality itself. The boundary of the bubble is like an eraser moving across a chalkboard, wiping out everything in its path. If such a bubble formed, it would expand at the speed of light, and we would never see it coming. From our perspective, one instant the universe would be here, and the next instant it wouldn't. This might sound like pure science fiction, but it's grounded in real mathematics. The bubble of nothing is a valid solution to certain versions of Einstein's equations, when combined with extra dimensions. It shows that even space-time isn't immune to decay. While most physicists don't think this is likely in our universe, it's a sobering reminder that our assumptions about stability might be fragile. The bubble of nothing idea also overlaps with the concept of vacuum decay we saw earlier. In that case, the danger is that our current vacuum is only metastable, and a lower energy vacuum could form a bubble that expands across the universe. The difference is that vacuum decay still leaves behind a universe, just one with different laws of physics. A bubble of nothing, by contrast, leaves behind nothing at all. It doesn't replace reality with a new one. It deletes reality entirely. Philosophically, this is hard to wrap our minds around. We're used to thinking about change as one state replacing another. Heat turning to cold, water freezing to ice, particles transforming into other particles. But the bubble of nothing would be change without replacement. It's the absolute termination of all states. If the vacuum is usually seen as potential, the womb of existence, then the bubble of nothing is the opposite, annihilation of possibility itself. It's worth emphasizing that, so far, there's no evidence that our universe faces this fate. Most versions of the standard model of particle physics and general relativity don't predict bubbles of nothing. The idea mostly arises in speculative theories with extra dimensions. Still, the fact that it's possible within some frameworks tells us something important. Even space-time, which we often take as the unshakable background of everything, might not be eternal. This connects to a bigger theme in physics, the recognition that many things we once thought were absolute, space, time, even nothingness, turn out to be dynamic and contingent. Aristotle believed a void was impossible. Later thinkers proved a vacuum could exist but treated space as a fixed container. Einstein showed space was flexible, bending under mass and energy. Quantum theory revealed it was seething with fluctuations. And now, speculative models suggest it might even disappear entirely. At every step, nothing becomes stranger and less stable than we thought. The bubble of nothing also highlights an important point about the limits of knowledge. If such a bubble did form, we could never detect it before it reached us. There would be no warning, no signal, no chance to prevent it. This means the possibility of ultimate annihilation is both untestable and unavoidable. We can't know whether it will happen, and if it does, we won't be around to analyze it. It's a reminder that some aspects of nothingness are not just puzzling but beyond the reach of science. Still, ideas like the bubble of nothing aren't just doom and gloom scenarios. They push us to rethink what we mean by existence. If space-time itself can decay, then reality isn't guaranteed. It's contingent on deeper structures we don't yet understand. That opens the door to new theories of quantum gravity, string theory, and the multiverse, where nothing and something blur in ways we can barely imagine. So while the bubble of nothing remains a speculative possibility, it forces us to confront the ultimate version of nothingness. Not a vacuum full of fields, not a different universe with new laws, but the erasure of reality itself. And in doing so, it shows just how far the concept of nothing has travelled, from Aristotle's rejection of the void to the most extreme frontiers of modern physics. After all we've covered, the ancient debates, the quantum vacuum, dark energy, and even the possibility of space-time collapse, we're left with a deceptively simple question. Is true nothingness possible? Can there ever be a state that is completely and utterly empty, without space, without time, without laws, without potential? Or is nothing always, in some sense, something? Physics, as it stands, seems to resist the idea of absolute nothingness. Even when we strip reality down as far as we can, we're left with structures. Remove all matter and radiation, and space-time remains. Try to remove space-time itself, and theories like quantum gravity suggest that something else, a more fundamental framework, takes its place. Even the vacuum of quantum field theory, often called empty space, is seething with fluctuations and energy. Instead of reaching nothing, we keep finding deeper layers of something. This is why many physicists argue that true nothing, in the strictest sense, may not exist. If reality has always had some kind of framework, then asking for absolute nothing is like asking for a square circle. It's a contradiction built into the definition. Our very language presupposes existence. To describe nothing, we inevitably smuggle in concepts of space, time, or potential. Even saying there is nothing treats nothing as a kind of there, which is already something. That said, Some thinkers do try to imagine absolute nothingness. One version is to think of it as the absence not just of matter and energy, but of the laws of physics themselves. If there are no laws, then nothing can happen. No fluctuations, no fields, no dimensions. But here's the paradox. If truly nothing existed, then how could it ever give rise to something? To talk about the universe emerging from such a state is to sneak in a hidden structure, the possibility of emergence. In other words, absolute nothing may be unthinkable, not because it's impossible, but because thought itself requires something to think about. This leads to a subtle distinction between two types of nothing. The first is the physical vacuum, what science studies. This is the lowest energy state of fields, the baseline of reality, full of fluctuations but devoid of matter. The second is philosophical nothing, the absolute absence of being, with no properties at all. Physics can describe the first but seems powerless to reach the second. Some philosophers argue that this shows science can never fully answer the question of why there is something rather than nothing, because science always assumes something. Even so, the line isn't always clear. For example, when cosmologists say the universe might have arisen from nothing, they often mean from a quantum vacuum state, governed by laws but containing no particles. To a physicist, that's as close to nothing as you can get. To a philosopher, it's still something, just a very thin something. This gap in definitions creates confusion, especially when the question makes its way into popular discussions. So is true nothing possible? We might frame the answer like this. Physics has no evidence for absolute nothingness. Every time we peel back a layer, we find structure. Every time we say, this is empty, we discover activity. Space is dynamic, fields fluctuate, and the vacuum has energy. If nothing means the absence of all that, then it may not be part of the universe at all. It may not even be a coherent concept. But the question refuses to die because it's tied to the deepest mystery of existence. Why is there something rather than nothing? If absolute nothing is impossible, then something must exist necessarily, whether it's space-time, quantum fields, or deeper structures we don't yet know. If absolute nothing is possible, then the fact that something exists at all becomes even more startling, demanding an explanation we don't have. Either way, the puzzle points to a limit of our understanding. Perhaps the most honest conclusion is that absolute nothing is not accessible to science. Physics can study vacuums, fields, fluctuations, and energy. It can show us how universes evolve and maybe even how they begin. But whether true nothing exists or could exist is a question that may sit forever at the border between science and philosophy. It's not just about the limits of the universe, it's about the limits of what we can know. After travelling through centuries of science, from Aristotle's rejection of the void to quantum fluctuations in empty space, it's worth circling back to philosophy. Because even with all our physics, the question of nothingness is not just a technical one. It's also a question about meaning, existence, and how we think about being itself. Philosophers have long argued that to understand something, we have to grapple with its opposite. The German thinker Martin Heidegger famously asked, "Why is there something rather than nothing?" He thought this was the most fundamental question of philosophy because it forces us to confront the fact that being exists at all. For Heidegger, nothing wasn't a void to be measured, but an experience that reveals being itself. When we confront nothingness through anxiety, mortality, or reflection, we come face to face with the strangeness of existence. Jean-Paul Sartre, writing a generation later, took a similar but more existential turn. In his book Being and Nothingness, he argued that nothingness is built into human consciousness. To be aware of what is, we must also be aware of what is not, what is absent, what could have been, what might be otherwise. Nothingness, in this sense, isn't out there in the universe, it's inside us, as part of how we make sense of reality. Our ability to imagine a future, to regret the past, or to conceive of possibilities all relies on an awareness of what isn't present. Eastern philosophy offers yet another perspective. In Buddhist thought, emptiness, shunyata, isn't the absence of being but the absence of inherent essence. Things exist but not independently. They are empty of a fixed self-nature because they arise only in relation to other things. This view reframes nothingness not as a threatening void, but as a way of seeing the world more clearly. Emptiness is not a lack but an interdependence. The Western anxiety over nothing is, in this framework, misplaced. It's not about erasure but about connection. All these perspectives highlight a critical point. Philosophy often treats nothingness less as a physical state and more as a contrast, a way to illuminate being. Without the idea of nothing, we might not even be able to articulate what it means for something to exist. In this sense, nothing is a conceptual tool. It frames our thoughts even if it never appears in the world. What makes this fascinating is how much it overlaps with modern physics. When scientists say the vacuum isn't truly empty, they're echoing something like Heidegger's view, that nothingness reveals something deeper about being. When quantum theory shows that absence is always filled with fluctuations, it resonates with Buddhist emptiness. What looks empty is actually full of interdependent activity. And when existentialists tie nothingness to possibility, it aligns with cosmology's view of the vacuum as potential, the seedbed of new universes. Of course, philosophy and physics don't always speak the same language. A physicist's nothing might mean a quantum field in its lowest energy state, while a philosopher's nothing might mean the negation of being itself. Mixing them carelessly can cause confusion, but taken together, they enrich the conversation. Physics asks what nothing does. Philosophy asks what nothing means. Both questions are necessary if we want a full picture. This also explains why the question, why is there something rather than nothing, remains so powerful. Science can show us how something arises from a quantum vacuum or a false vacuum, but it may never answer why there is a vacuum at all. Philosophy can ask why nothing should be impossible, but it can't measure fluctuations or dark energy. The two approaches meet in the middle, circling a mystery that refuses to go away. Ultimately, philosophy reminds us that nothingness is not just a scientific curiosity, it's an existential reality. When we think about our own lives, we measure them against non-being. The fact that we weren't here before birth and won't be here after death. When we wonder about the universe, we frame it against the possibility that it might not have existed at all. Nothing is the backdrop against which meaning, being, and value come into focus. So even as physics digs deeper into the structure of the vacuum, philosophy keeps us grounded in the human side of the question. Nothingness isn't just a feature of the cosmos, it's a feature of how we make sense of existence. And that means our exploration of nothing will never be purely scientific or purely philosophical. It will always be both. Few questions push the limits of science and imagination more than this. What, if anything, came before the Big Bang? The moment we ask, we're immediately tangled in paradox. Time itself, according to general relativity, began with the Big Bang. If that's true, then asking what happened before is like asking what's north of the North Pole. It doesn't make sense within the framework of the question. And yet, the human mind insists on asking, could there have been a state of nothingness before everything began? For much of the 20th century, the dominant view was that the universe had no before. The Big Bang wasn't an explosion in space, it was the expansion of space itself, from an initial singularity, where our known laws break down. In that picture, time begins at the Big Bang, so talking about a prior state is meaningless. If that's right, then there was no nothing before the universe because there was no before at all. Nothing wasn't an empty waiting room for the universe, it simply wasn't. But not all scientists are satisfied with that answer. Some argue that the singularity at the beginning of time is a sign that general relativity is incomplete. At extremely high densities, quantum effects should matter, and we don't yet have a complete theory of quantum gravity to describe what happens. That opens the door to new possibilities about what came before the Big Bang. One idea is that the universe emerged from a quantum vacuum through a process similar to tunneling. In this scenario, what we call nothing is actually a state without classical space and time, but still governed by quantum rules. From that nothing, fluctuations could produce a tiny bubble of space-time, which then expanded to become our universe. This is sometimes called creation ex nihilo in physics, not from absolute nothing, but from a quantum state that looks like nothing compared to our everyday world. Another proposal is the cyclic universe. Instead of beginning from nothing, the universe goes through endless cycles of expansion and contraction. What we call the Big Bang would then be a bounce, a transition from a prior universe collapsing into a singularity and rebounding into a new expansion. In this model, there is no absolute nothing, just an eternal chain of somethings, with each cycle giving rise to the next. Then there's the multiverse idea. Inflation theory, which explains the early expansion of the universe, also suggests that inflation might not stop everywhere at once. In some regions of space-time, inflation continues indefinitely, creating new bubble universes. If that's the case, then our Big Bang was just the beginning of our bubble, but it wasn't the beginning of everything. The before wasn't nothing, but rather a larger inflating background that keeps spawning new universes. Still, even if these models avoid an absolute beginning, they don't fully answer the question. If our universe came from a quantum vacuum, why does that vacuum exist? If the cosmos is cyclic, why does the cycle itself exist? If there's a multiverse, why is there a multiverse instead of nothing? At some level, the puzzle remains. Why is there something rather than nothing at all? Some philosophers and scientists suggest that this might be the wrong question. If time itself is a property of the universe, then asking about a before may simply not apply. The Big Bang might be the boundary of time, not the beginning in the usual sense. Nothingness before the universe may not exist because before is meaningless. Others go further, suggesting that nothing might be unstable. If absolute nothingness were possible, it might not stay that way. Just as a ball balanced perfectly on a hilltop will eventually roll down, nothing might decay into something. In this view, existence is inevitable. If nothing is allowed, it will always produce something. And the fact that we live in a universe is simply what nothing does. But here's the catch. These are speculations. We don't yet have empirical evidence that tells us what, if anything, came before the Big Bang. We only know that as we rewind the clock, our equations break down at the singularity. Beyond that, we're in uncharted territory. So, was there nothing before the Big Bang? According to standard relativity, the question has no meaning. According to some quantum theories, the universe might have tunneled into existence from a vacuum-like state. According to cyclic or multiverse models, something always existed, in one form or another. The debate continues because each possibility points to a different version of nothing. And maybe that's the real lesson here. When we ask about nothing before the Big Bang, we're really asking which kind of nothing we're talking about. Absolute nothing, without time, space, or laws. A quantum vacuum, bubbling with potential. Or just the absence of our current universe within a larger structure. Physics hasn't given us a final answer yet, but it has shown us that nothing is far more complicated than it seems. So far we've looked at nothing in terms of beginnings. But what about endings? If the universe has a future shaped by the vacuum, then nothing may also play the central role in how everything eventually fades away. The fate of the cosmos isn't just a matter of stars burning out and galaxies drifting apart. It depends on what nothing really is and how it behaves. One possible future is known as heat death. In this scenario, the universe keeps expanding forever. Galaxies grow more distant, stars exhaust their fuel, and black holes eventually evaporate through Hawking radiation. Over unimaginable stretches of time, matter and energy thin out until the universe approaches a uniform, near-empty state. It never quite reaches absolute nothingness, but it gets close. A cold sea of extremely low-energy photons and particles spread so thinly that no structures can form. In this version of the future, nothingness wins not by erasing the universe, but by diluting it into near invisibility. Another possibility is tied to dark energy. If the vacuum energy driving cosmic acceleration stays constant, the universe will keep expanding at an accelerating rate. Distant galaxies will slip beyond our horizon, becoming forever unreachable. Over trillions of years, even nearby galaxies will be torn apart from view. The observable universe will shrink to a lonely island of stars until those too fade away. In this picture, nothingness creeps in through isolation. Space doesn't disappear, but our access to it does. Eventually, all that remains is emptiness from our perspective. But there's a more dramatic version of this story, sometimes called the Big Rip. If dark energy isn't constant but grows stronger over time, the expansion could accelerate so violently that it rips apart galaxies, then solar systems, then even atoms themselves. In this fate, the vacuum doesn't just isolate, it destroys. Space expands faster than structures can hold together, leaving behind a universe of shredded particles. And then perhaps nothing at all. There's also the spectre of vacuum decay. If our universe's vacuum is metastable, as some Higgs boson measurements suggest, then someday a bubble of lower energy vacuum could appear. This bubble would expand at nearly the speed of light, rewriting the laws of physics inside it. To us, it would look like instant annihilation. From a cosmic perspective, it would be a transition to a new reality. In this scenario, nothingness doesn't arrive gradually. It arrives suddenly, replacing our universe with an unfamiliar version. Of course, all of these scenarios are projections based on what we currently know, and what we know is incomplete. Dark energy, which drives the acceleration, is still mysterious. We don't know whether it's constant, changing, or even correctly understood. That means our predictions about the universe's fate are provisional. Still, what unites all of them is the central role of the vacuum. Whether the universe dies by heat death, big rip, or vacuum decay, the deciding factor is what nothing really is. It's striking to realize that in every case, the end doesn't come from something happening, but from something being absent. The absence of fuel in stars, the absence of matter in vast regions of space, the absence of stability in the vacuum. In a way, the story of the universe is the story of nothing slowly asserting itself. Matter and energy have their time, but in the long run, it's emptiness that dominates. This has a sobering but also profound implication. If nothing is the ultimate winner, then existence as we know it is temporary, a fleeting arrangement against the backdrop of the void. But at the same time, that makes existence even more remarkable. The fact that stars shine, galaxies form, and life emerges, all of it is carved out of a universe where nothingness could have ruled from the start. So whether the universe ends in a cold fade, a violent rip, or a sudden vacuum collapse, the void isn't just a background. It's destiny. Nothing isn't just where we might have come from. It's also where we might be going. For all our attempts to define, measure, and model nothing, there's a problem we can't escape. Every time we try to describe nothing, we turn it into something. The very act of talking about nothing forces us to smuggle in concepts like space, time, or possibility. This is the paradox at the heart of the idea. Take language itself. If you say there is nothing, you've already given nothing a kind of existence. You've made it the subject of a sentence, placed it in a location, there, and treated it as though it can be identified. Philosophers as far back as Parmenides pointed this out. If you can speak of nothing, then it's no longer nothing, because it has become an object of thought. For him, this was proof that nothing could not exist at all. Physics runs into the same problem, just in a different form. When scientists describe the quantum vacuum, they call it empty space, but then immediately explain that it contains fields, fluctuations, and energy. It's not really nothing at all, it's the lowest energy something. Even when physicists try to imagine absolute nothing, they end up using mathematical frameworks that assume laws of logic, probability, or quantum mechanics. And those laws are already something. This raises the uncomfortable possibility that true nothing may not be describable in human terms. Our brains evolved to deal with a world of things, objects, events, relationships. Trying to imagine the absence of all of that may be like trying to see beyond sight or hear beyond sound. We can say the word nothing, but the concept may be fundamentally beyond us. Another layer of paradox is that we often define nothing by contrast. Nothing is the absence of matter, the absence of space, the absence of time. But to define it that way, we need the concepts of matter, space, and time. Without them, nothing loses meaning. This makes it slippery. It exists only as the shadow of something else, not as a self-contained idea. Even mathematics, our most abstract language, stumbles here. Zero is often seen as the numerical representation of nothing. But zero is still a number. It has properties, relationships, and uses. In set theory, the empty set is sometimes called nothing, but it's still a set, defined by the rules of mathematics. The moment we formalize nothing, it becomes structured. We never really capture absence. We just create a symbol for it. This paradox isn't just abstract nitpicking. It has consequences for cosmology. When we ask whether the universe came from nothing, we risk confusing two very different ideas. Nothing as a physical vacuum state, which physics can study, and nothing as absolute absence, which physics can't. If we don't distinguish them, we end up with misleading claims. Saying the universe came from nothing can mean it came from a quantum vacuum, or it came from absolute non-being. Two very different statements. One belongs to science, the other to philosophy. The paradox also shows up in personal reflection. When people imagine nothingness, they often picture a black void, but that's already something. It's blackness, emptiness, a visual experience. True nothing wouldn't look black or white or any colour. It wouldn't look like anything, because there would be no perception, no space, no observer. Trying to picture it only produces another kind of something, a placeholder for absence. So where does this leave us? One possibility is that nothing is simply a limit concept. It doesn't refer to an actual state, but serves as a boundary for our thinking. We use it to point at the edge of what we can describe, like a warning sign at the border of a map that says, "Here there be dragons." In that sense, nothing is real, not as a physical condition, but as a marker of the limits of sense-making. Another possibility is that nothing has a deeper meaning in science than in everyday life. When physicists use the word, they are not claiming absolute absence, they're describing the most reduced state accessible to their theories. That might be why the vacuum keeps surprising us. It's not nothing in the strictest sense, but it's close enough to raise profound questions. Either way, the paradox of describing nothing is part of the reason the concept fascinates us. Every time we think we've captured it, it slips away, turning into something else. Nothing is both the simplest idea and the hardest to pin down. And maybe that's why it keeps showing up in philosophy, physics, and human imagination alike. Up to this point, we've been treating nothingness as a problem for philosophers and physicists. But it's also a deeply human concern. The question of nothing doesn't just belong in equations or abstract arguments. It connects directly to how we understand ourselves, our place in the universe, and even our own mortality. At the personal level, nothingness is tied to the boundaries of life. Before we were born, there was nothing of us. After we die, we return to nothing, at least in terms of physical existence. This fact makes nothing a constant presence in human thought, whether we acknowledge it or not. When people worry about death, often what they fear isn't pain but the idea of slipping into nothingness. Philosophers like Epicurus argued that this fear is misplaced. When we are, nothing is not. When nothing is, we are not. In other words, we never actually encounter nothingness. We only imagine it. Still, that act of imagining is powerful enough to shape how we live. On a larger scale, the universe itself confronts us with nothing. If most of the cosmos is dominated by dark energy, an energy of empty space, then our existence is taking place against an overwhelming backdrop of near-nothingness. Matter, stars, planets, and people make up a tiny fraction of reality. We are islands of something in a vast sea of almost nothing. That perspective can feel humbling, even unsettling, but it can also sharpen our sense of meaning. If being is rare against the backdrop of non-being, then it becomes all the more precious. There's also a creative side to nothing. In art and thought, emptiness often functions as possibility. The blank page is intimidating, but it's also freedom. The empty stage is a space where anything can happen. In this sense, nothing isn't absence, but potential. The same idea resonates in physics. The quantum vacuum looks empty, but it's full of potential, capable of producing particles, energy, and even entire universes. What looks like nothing may be the richest source of possibility there is. Different cultures approach this differently. In some Eastern traditions, emptiness is seen not as a threat, but as liberation. To recognize the emptiness of things, their lack of permanent, independent existence, is to be freed from clinging and fear. In that framework, nothingness is not the end, but the condition that allows change and connection. This contrasts with much of Western thought, where nothingness is often imagined as a void that threatens being. Both perspectives shape how people respond emotionally to the idea of nothing. For scientists, grappling with nothing is a reminder of humility. The fact that so much of modern physics hinges on the properties of the vacuum shows how little we really know. We once thought nothing was irrelevant. Now we think it drives cosmic expansion. But the details remain mysterious, and that mystery forces us to admit that our theories are incomplete. Nothing, ironically, keeps science grounded by reminding us of its limits. And for all of us, the idea of nothing pushes us to think about meaning. If the universe will one day fade into near nothingness, does that diminish our lives now, or does it make them more valuable? If existence is temporary, carved out against the backdrop of non-existence, then maybe the very fact that we are here at all is extraordinary. From that perspective, nothing doesn't diminish us. It makes us more aware of the fragility and rarity of being. So what does nothing mean for us? It means that absence and presence are intertwined, that our lives are framed by nothing, but also made meaningful by it, that science can reduce nothing to fluctuations and fields, but the human imagination will always find in it a mirror for our deepest questions. Nothing matters to us not just because it shapes the universe, but because it shapes how we think about ourselves. After travelling through philosophy, physics, and cosmology, we've seen that nothing is never as simple as it sounds. For Aristotle, the void was impossible. For Torricelli and Pascal, it was something you could create with a tube of mercury and a clever experiment. For Einstein, it became the flexible fabric of space-time. For quantum theory, it's a restless sea of fluctuations. And for cosmology, it may be the force driving the universe's beginning, expansion, and eventual fate. At every stage, the closer we look at nothing, the more it dissolves into something. The vacuum has fields, space has geometry. Even the absence of matter has energy. When scientists try to strip away the universe to its barest form, they find not emptiness, but activity. Nothing in physics keeps turning out to be a hidden layer of reality. But at the same time, the idea of absolute nothingness, the absence of space, time, laws, and possibility, still haunts us. It shows up in philosophy as the shadow of being. It shows up in cosmology when we ask what came before the Big Bang, or whether the universe could ever end in total erasure. And it shows up in everyday life, whenever we think about the boundaries of birth and death. This leaves us with open questions that may never have final answers. Is true nothingness even possible, or is it a contradiction in terms? If the universe came from nothing, what kind of nothing was it? A quantum vacuum, a false vacuum, or something beyond our comprehension? If the vacuum can decay, does that mean reality itself is temporary? And most fundamentally, why is there something rather than nothing at all? Perhaps the most humbling lesson is that nothing might always escape us. It may be beyond science because science can only describe something. It may be beyond language because words always smuggle in assumptions of existence. And it may be beyond imagination because our minds evolved to deal with a world full of things. Nothing might be the ultimate limit of human thought. And yet the pursuit of nothing has been one of the most fruitful journeys in science. By asking what nothing is, we've discovered quantum mechanics, relativity, dark energy, and the very structure of the cosmos. By wrestling with absence, we've uncovered the richness of presence. In a strange way, nothing has given us everything. So maybe the real value of nothing is not in finding a final definition, but in keeping the question alive. Nothing forces us to confront the edges of knowledge, where physics, philosophy, and human meaning all meet. It's a reminder that even in the vastness of the universe, some mysteries will always remain, and that our search for answers is itself part of what makes existence meaningful. In the end, perhaps nothing is not the opposite of being, but its silent partner. Without nothing, there would be no contrast, no frame, no reason to marvel at what is. And maybe that's the deepest truth of all. Nothing is what makes something stand out.